In this example problem, we'll be looking at finding the velocity, position, and acceleration of some object if you know the position vector as a function of time. We're specifically going to find these three quantities at 2 seconds, which is a sort of an arbitrary time to show you how you can find it at any time. Now, the key relationship here in general is going to be that the velocity vector is the derivative of the position vector with respect to time, and the acceleration vector is the derivative of the velocity vector with respect to time. But you're probably not familiar with taking derivatives of vectors, so I'm going to show you explicitly how to do that. Now, the position at 2 seconds is straightforward. All you have to do is plug in 2 seconds. So that's 3 meters per second squared times 2.0 seconds squared plus 5 meters I hat plus 8 meters per second cubed times 2.0 seconds cubed j hat plus the last one, which is 9 meters times sine of 2 pi times 2 seconds over 12 seconds plus pi over 2 k hat. Now I just have to plug those into a calculator. What you get if you do that is 17 meters I hat plus 64 meters j hat plus 4.5 meters k hat. So that's one of my answers. When I want to find the velocity at that same time, I have to take the derivative of the expression before you plug in the time. Because remember, the velocity of 2 seconds means take the derivative and then plug in 2 seconds, not the other way around. So if I take a derivative of a vector, I'm going to take the derivative of each component separately. So I take the time derivative of the first part, that's just a polynomial. The derivative for a polynomial brings down the power, so the 2 would move down, and then just one less on the power, so it would be 2 times 3, so that would give me 6 meters per second squared times the time, and then the extra 5 meters just drops out of the derivative because it's a constant. Similarly, I get 3 times 8, which is 24 meters per second cubed times the time squared, plus, when I take the derivative of sine, I get cosine, so 9 meters times cosine of 2 pi t over 12 seconds plus pi over 2. But I also, from the chain rule, have the derivative of the inside, and the derivative of the inside is going to get rid of the t and the constant part, so I get 2 pi over 12 seconds. When I plug that in, 2 seconds into there, so I get v of 2.0 seconds, and I'm not going to explicitly show plugging in 2 seconds in each of these t's, but I'll just plug in what you get from the calculator. That is 12 meters per second I hat plus 96 meters per second j hat minus 4.1 meters per second k hat. So notice that, excuse me, box this. Notice that the units change because when you take the derivative, every power of t decreases by 1 in the polynomials, and the derivative in the sine function also brought out a factor of 1 over seconds as well, so that these are in meters per second rather than in meters, which is what you would expect for a velocity. Now the acceleration, as a function of time, I can just go through to the same thing, derivative of each of the components. When I have a constant like that, I just get 6 meters per second squared times I hat, because the t goes away, plus I bring down the 2, and I get 48 meters per second squared, so cubed, times the time, j hat, oops, I was missing a j hat here, oops, plus 9 meters per second. Now derivative of sine is now negative cosine, so I'm going to pull out that negative sign, and then that leaves me with sine of 2 pi t over 12 seconds plus pi over 2. I still, from before, have a factor of 2 pi over 12 seconds, but now I bring out an additional factor of 2 pi over 12 seconds from the chain rule again, so that gets squared times k hat. And if I plug in 2 seconds, again, I'm not going to bother to write 2 seconds everywhere there's a t, but that's what I would do. I'll get 6 meters per second squared. I hat, when I plug that in, I get 96 meters per second squared. J hat, no, because the 2 seconds cancels out 1 power of the seconds in the denominator there to give me seconds squared. And then I get minus 1.24 meters per second squared k hat. And the point of this example is not really this particular function or the particular time. The idea is that if you have a position vector as a function of time, you can always take the derivatives of it component by component and plug in the time to find the position, velocity, acceleration, or any higher derivatives at any time. So if you take a derivative of a function, then you can find the velocity and position from a position function. I would say velocity and acceleration from a position function. Similarly, you can go the other direction. I could have given acceleration versus time, and then you'd have to start integrating. Now, the one thing is that you could do a constant of integration each time. So each of the components would have an extra plus constant in there, which you would have to either know the value of the function at some time, so like the velocity. So say if you had acceleration and you said, I know that at 3 seconds my velocity function vector equals something I hat plus something j hat plus something k hat. Then you could go through and then you could solve for the constant because all the x components have to be equal and the y and the z separately. And you can take the derivative again to get position. Oh, sorry, integral again to get position. So to go in sort of this direction is an integral, and that direction is a derivative.